Hello, Longhorns. It's Dr. Kelly again. Today we're going to take a look at the next section in our lesson that deals with impulse. And I want you just to take a second to look at our first slide and tell me what's happening in the picture. So, as you can see, we have a soccer player that has brought a soccer ball to rest. So, the velocity of this ball, of course, is 0 meters per second. If you think about it, we've been talking about momentum, and momentum was represented with the letter P. P equals M times V. So momentum was equal to mass times velocity. When you think about impulse, I want you to kind of go back and think about Newton's second law. Force equals mass times acceleration. We're going to put together some of those smaller equations we learned during the first semester in the second 9 weeks. And we're going to move those over to how they really apply to your momentum and, of course, your impulse, because this is our new theory. Let's imagine that this soccer ball was initially in motion. The soccer player saw it coming his way, runs up, places his foot on the ball, and makes a stop. The ball was in motion, so it had momentum, and now it doesn't. There's a difference in the application of force, and there's a difference in the amount of time that force has been applied. It's kind of where our lesson is going. So, impulse and momentum, we're going to put these two together, and we'll see exactly how that turns out for us. First things first, we remember Sir Isaac Newton. His second law was force equals mass times acceleration. If you remember, force is measured in newtons, mass is measured in kilograms, acceleration was measured in meters per second squared. If I look at Newton's second law, we also learned first semester that acceleration had its very own equation. So acceleration is equal to velocity divided by time. Well, what happens when we kind of melt these two together? If I take Newton's second law, we remove the letter A, and instead of A for acceleration, we just input the part of the equation that should be there. Velocity divided by time. Time is going to move over, and this is going to be your momentum impulse theorem. We're looking at how force and time can be equal to mass times velocity. Now here's a question. What equation did we learn in the last video that had M times V? That's right, momentum. So this is your equation for momentum. This is our derived form that came from the other side as we talked about Newton's second law. Impulse is going to be measured in Newton seconds. And of course, you remember that momentum is measured in kilograms times meters per second. Now, here's your new equation of the day. Remember or recall that the delta sign means there's a change in. So an object could have started in motion, let's say at 15 meters per second, but then it came to rest. Well, my V initial would be 15 meters per second. My V final would be 0 meters per second. And for your change in V is V final minus V initial. We will always subtract. Here's another good example you guys can read over as you're going back through your PowerPoint. And you're looking at a change in momentum based on the amount of time. Maybe you didn't move quick enough. And momentum changes based on the amount of force that was applied. Here's a secondary example that shows that we have a truck that has a pretty nice mass, a pretty consistent velocity, and when it comes into contact with the hay, the truck is going to win. Now, same truck, but this time, let's put a wall there. Does the wall have the same properties as that stack of hay? The answer is no. So in this example, the force that's being applied wasn't quite enough, so the truck didn't win. Here's a practice problem as we're moving through pages 195, 196, and headed toward the end of chapter 6 in your textbook. So this is one of the first problems that's going to pop up, and I'll read it to you. We have a 1,400 kilogram car moving westward with a velocity of 15 meters per second. Collides with a utility pole and is brought to rest in 0.3 seconds. Find the force exerted on the car during the collision. Once you make it to your impulse momentum theorem, it is good to remember that the guess method will be your best friend. We're going to have a number of variables, and remember that the guess method, of course, has 5 steps. So for my letter G, they gave me mass, 1,400 kilograms. I have my initial velocity, which is 15 meters per second. Remember that velocity is a vector. So if you make east positive, it means that west has to be negative. And that's where our negative sign here came from. It's based on direction. My time was 0.3 seconds, and my final velocity was 0 meters per second because it was brought to rest. What would be your unknown for this particular problem? If I look up here in my second sentence, find the force. Capital F will always be used for force. Our equation is going to be the new one that we learned. So we're going to use force times time, and then we have your mass and velocity, both your V initial and your V final. We take our equation. There's no reason to really move very much around for us. No substitutions are needed because all of our units are looking pretty good. And we're going to simply go in and plug in our numbers. Mass times our final velocity, since we came to rest, was 0, minus the mass of the car multiplied by the initial velocity divided by time. This side of your equation is pretty much going to disappear because anything multiplied by 0 will be 0. 1400 times negative 15 meters per second is going to give you 21,000. Now, you may be wondering, where did your negative sign go? Remember, the negative sign, you have a negative here and a negative there, but the negative sign is really only telling us direction. So it lets us know my east direction was considered positive. West is going to be negative. When I divide, my answer will come out to 70,000 newtons. And if you want, you can always put 70,000 newtons westward, since west would be your negative direction. Another way to put it is if you left the number negative, and you'll sometimes see a small symbol or a compass behind it, which lets you know the number itself is just giving you direction. Let's work a second example. This is the first practice problem in your textbook. So do me a favor. I want you to read the problem, pause the video, use the guess method, and let's see exactly how we end up in the very end. We have a 0.50 kilogram football is thrown with a velocity of 15 meters per second to the right. A stationary receiver catches the ball and brings it to rest in 0.02 seconds. What is the force exerted on the ball by the receiver? Whew, pretty big one. So let's use our favorite method because it's a good way for us to figure out what we already have and exactly what we are going to need. My first step in my guess method is the letter G. Let's look for our given information. A 0.50 kilograms. If it is measured in kilograms, it is your mass. Football is thrown with a velocity of 15 meters per second to the right. If it's going for 15 meters per second, it will be positive since it's headed to the right. If it was going to the left, it would be negative. A stationary receiver catches the ball and brings it to rest in 0.20 seconds. Brings it to rest. What is my it? I think that's going to be your ball. So 15 meters per second is my the initial velocity, and the final velocity is 0 meters per second. It took 0.2 seconds, which is time. Ooh, be careful on your numbers. I would have left a 0 out, which would have changed my place value and changed my answer in the end. What is the force exerted on the ball by the receiver? So your unknown is force. We've been given mass, your initial velocity, final velocity, and time. Next step, what equation is probably going to be our best equation? Well, your equation may start out looking a little like this one. Force times time will equal the letter P. If you remember, what is the equation for momentum? That's right. Under my substitution step, we're going to make this a little bit bigger. force times time, and we know that P is equal to mass times velocity. So we're going to have M times V. Well, we're looking for force. If I'm looking for force, which is here, T is going to have to move. Right now, force and time are being multiplied. In order for me to move T, or time, to the other side of the equal sign, I'm going to do the opposite. They have multiplied. I will divide both sides by T. Those are going to cancel out. My new equation will be force equals mass times velocity divided by time. Well, what happens when we have two velocities? Remember, there's normally a delta sign in front. So we're going to do V final minus V initial. Let's plug in our numbers for our last step, which is solve. We're looking for force. My mass is 0.5 kilograms. The velocity, we have V final minus V initial, which that's going to turn that into and then of course you have time. This negative sign is simply telling you that you're moving in the opposite direction. Let's multiply and see what we get on top. So if we say 0.5 times 15, our answer will be 7.5 divided by 0.02. 7.5 divided by 0.02 will give me negative 375 newtons, or most would say 375 newtons to the left, because you're going in the opposite direction. All right. As you're walking through your steps, I want you to be very careful with your given information.